But yeah, all right, great. Start. So this is where we ended last time. I started talking about the gradients for the unitary transformations in order to optimize amplitudes. Technically, one, I would love to have gradients so that we could lower the energy using the gradients. And in general, it's not a straightforward task. Depends on the generator that we need to take the gradient of the amplitude with respect to. And there are simpler cases where the generator that we are considering has only, say, two eigenvalues, plus minus 1 or plus minus lambda. And then in that case, there is this parametric shift rule that was suggested, and we discussed how it works. So to finish that section, I wanted to discuss a little bit of possible generalizations of the parametric shift rule to more general cases where generators, they have more than two eigenvalues. So that's the kind of the idea of this subsection. Now, actually, this work that I will talk about, the total generalization, came out as a result of just seeing, I guess, the work of my colleague Alanas Paraguzik and his student Abhinav Anand. So I was a committee member for Abhinav, and when he was describing what they did for unitary coupled cluster theory in disentangled form, I kind of thought that it would be nice to kind of generalize this idea even further. But what they did in 2020, essentially they found that, okay, if we want to use something like parametric shift rule for UCC hierarchy, right? So their generators, they don't have just two eigenvalues. And surprisingly, actually, for me at least at that time, it can be shown that any, not just the single excitations or double excitation, de-excitation, but n-tuple, up to n-tuple excitation, de-excitation, they only have three eigenvalues. So plus minus 1 and 0. Okay, so that's something that one can show. All right, so then if generator has three eigenvalues, not two, formulas become more complicated. And they derive those formulas using projectors. Here they shown that okay, generator can be essentially represented as a projector on the. Actually, we'll use this formula later in more general form, that any operator, if you have eigenvalues for the operator lambda i's, right, corresponding eigenvalues always have projectors or sort of subspaces. And so you can always write G as a projector to the subspace multiplied by corresponding eigenvalue. Right, so that's just eigen decomposition. This is what they did here. So this is for plus 1, minus 1, and 0, of course, cancels the projection. So you get instead of one exponent projectors, they commute. So you can get two exponents. And then for each, you could use potentially shift rule. And that allows you to get the expression for the gradients as 4 expectation values. But it turns out that, yeah, essentially, you could also write the exponential function of generator like this. Not surprisingly, it's just some polynomial of here we use up to linear g and p0, but p0 could be substituted by kind of quadratic function of g. So essentially, you will have a quadratic polynomial for the exponential function. And then there is some extra algebra, which I don't want to go into, but in the paper, one can see is that for the real wave functions, there are some extra simplifications, and then eventually you could get with just two expectation values. So indeed, for the unitary couple cluster theory, the parametric, essentially in parametric shift rule, we have two expectation values for each gradient, and these generators for the real wave functions also allow you to use some, they call it fermionic shift rule, that also have just two expectation values essentially, right? So it's not bad. But what I was thinking is just, okay, well, these are formulas that are quite different from each other. Can we do some kind of generalized way of deriving those formulas? And the reason is that there are some still generators that use either in machine learning approaches mostly. I'm not very familiar where exactly people want to use that, but I know that there are something like transmon gates and match gates corresponding to these generators, and they generally have 4 eigenvalue, 2-qubit gates. In general, if you have 2 qubits, any operator will have at least 4 eigenvalues. And then there is another motivation more related to chemistry. If we want spin conserving generators, sometimes these generators they have more elements in them, and actually the number of eigenvalues grow beyond 4. It's like we'll see at the end. I think we've done for the relatively general 2-electron excitation up to 16 different eigenvalues. So figuring out how to do some version of parametric shift rule for that was of interest. Essentially, these are just some examples that we know. Maybe later there could be a new suggestion on the best way to create the unitaries with kind of some generator, and so we want to be able to do the gradients. Essentially, that was the motivation. And there are 2 directions. One is already I was kind of explaining that these gradient formulas, they are like formulas for the differentiation of the functions that we do in numerical analysis on a classical computer. And the numerical finite difference formulas, they are always exact for finite degree polynomials. And the same intuition could be applied here, where instead of final polynomial, what is happening is that if generator has L eigenvalues, then it's actually always possible to present exponential function of that generator as a L-1 degree polynomial, right? And we'll see how the coefficients here, the A and theta, those are the coefficients that can be obtained using linear system of equation. So it's relatively straightforward. And then turns out that there is yet another approach, which what we do in it is just decomposing the generator in linear form, like as a linear combination of operators, and those operators are somewhat simple. They have a low number of eigenvalues. So to be specific, you could always think, okay, if you have a generator, you can always write it as a linear combination of Pauli products, and Pauli products always have just 2 eigenvalues, plus and minus 1, right? And so we could kind of try to apply shift rule for this parts and somehow get the essentially gradient for the G. And the hope there is that linearity of the gradient in general will allow us to do that. But of course, I'll show in a moment like how can this be done. All right. And so here we assume also real coefficients in that expansion. And that's not a problem because this is anti-Hermitian, so whatever complexity appears in the coefficients, it can also be always put in the, at least in Pauli products. If you multiply them by I, then they stay involutory. Okay, so the number of eigenvalues doesn't change. All right, so let's look at the first polynomial expansion case. So what's going to be the result of this formula for the gradient is simply a linear combination of expectation values that are written there. So effectively, if we want to have a gradient of energy at the value, say amplitude of tau, we need to add theta n shifts and then some differently shifted expectation values with some coefficient Cns, right? So there are two quantities to find in general: the coefficients and the shifts, okay, for every gradient. And okay, so we have a lot of parameters essentially to find, but the idea of those parameters is to give us gradient, and we know that the gradient in general is written like this. So what we have is just a single g, just on the different sides of the h. So one is on the left, and other is on the right, right? And so because we are working with generators that only have L eigenvalues, so every exponent here can be decomposed into polynomial function, right? And so every shift will give us polynomial. There will be n degree polynomial on the left of the Hamiltonian, n degree polynomial on the right Hamiltonian, on the right side of Hamiltonian. And what the idea of these coefficients will be is to do the cancellation so that only linear parts will be left, right? So we could always find enough coefficients, zero the higher powers that are appearing on the left side of the Hamiltonian, right side of the Hamiltonian, and only will be left with the like a G part. That's the same idea as in the case of parametric shift rule, where this was simply a constant plus linear in G. We still, in that case, needed to remove the constant part and remove the quadratic part where G appears on the left of the Hamiltonian and on the right Hamiltonian. So we needed to cancel that, right? And that was that was the standard parametric shift rule that required the coefficients. Okay, so we have to find this first. For any generator, we have to find this coefficients A in the parametric, in polynomial decomposition. And I think in general, this is a useful exercise to know how to do it, because in quantum computing or in general in quantum mechanics, sometimes we want to work with operators that are non-polynomial. And it's good to know that if you have finite spectrum of the generator, you could always present it as a polynomial of generator. And the question could be, how do you really find this expansion in some sort of straightforward way? And then we will, once the expansion is found, we need to find the coefficients that essentially remove the higher powers of G, so that the only linear G are left, right? So that's the second step. All right, how is it done? We start with this expression for any generator in terms of projectors. So projectors that we have, they are nice in the sense that kind of square of the projector is a projector itself, and they are orthogonal, so means they don't overlap. Okay. And so if you do that, you could you could always sort of see that if you have projector expansion, then the exponential function of the Hamiltonian, the generator is simply expression over there, because you could lower the projectors from the exponential form to linear form, because the high powered projectors always give you back the linear part of the projector, right? And then what you want to do is you want to sort of compare the expression that you want to get. That can be also written in terms of just substituting G with projector like this, right? And since we have on the right hand side in both expressions projectors, so then we could just correspond each term, right? So for each Pn. So if we do that, so for every n, essentially on the top expression we have this exponential form, but with the eigenvalues, and on the left side, we have this part for each n, and it contains the coefficients that we want to know. I is just the, it's known imaginary unit, right? And I get eigenvalues and eigenvalue in the power of k, right? So this is a linear system of equations that one can think of as like ax equals b, right? Where the b part would be just this exponent of I lambda n theta, right? And then the A matrix is Vandermonde matrix, which is lambda n k, and then multiplied by I to the k part, right? So this is element n k, and then x is the set of coefficients that we want to find, right? So this is the guy Vandermonde, whose name is kind of related to that matrix, and it appears in some other problems as well, like mostly interpolation with polynomials. But here it's just you need to invert the Vandermonde matrix, and if the eigenvalues are different, then it's always invertible. So the solution simply is the inverse of Vandermonde. Like you could also put the I there, and this is the expression for the coefficients, right? So now you know if you have any exponential function of the operator with a finite spectrum, you could always write it as a polynomial with the coefficients given by this expression. And of course, the problem with Hamiltonian, if you want to do this for the Hamiltonian, is that we don't know eigenvalues of the Hamiltonian in general, and also the number of eigenvalues is large, so the polynomial will be exponentially long. Okay, so that will not work for the complicated operators, but it always will work for simple operators. Okay. All right, now the second part is actually very similar to the first. We just need to cancel some like terms. If we put instead of exponential functions now the polynomial expressions, naturally we'll get this g into the powers of k prime and k from the left and right side of the Hamiltonian, right? And then I combine the coefficients of two expansions in one giant coefficient, large A, right? And then the whole purpose of Cn is to make sure that we get instead of all the different powers, just this linear terms. You only want g from each side, and then again it becomes a question of solving linear system of equations, where the right-hand side is just really fixed. Oh no, okay, it's good. Right. So with this b's, where only 0, 1 and 1, 0 should be constant I, and then others are 0. And so then essentially we could get the result, get the coefficients. Let me go back a little bit. Yeah, so here solving this system of equations is of course not a problem for any reasonable number of eigenvalues, and it gives the final expression with generally L square coefficients. That's what is needed here. So if you have L eigenvalues in the generator, in order to get the gradient, you need L square expectation values, which is not a nice scaling. And in many generators, the eigenspectrum is symmetric. So it turns out, well, like as we saw in the case of, say, unitary couple cluster theory, that's a plus, minus 1 and 0. So because of that symmetry, you can actually go from L squared to L squared divided by 2, but still the number of expectation value grow quadratically. And yeah, for more complicated generators, it becomes sort of expensive to calculate all these expectation values. Now we will see that it's not worth doing this expression for L more than 2 or 3, because the other way, where we essentially decompose the Hamiltonian, the generator into some simple operators which contain only like 2 or 3 eigenvalues, that way is potentially even better in terms of the scaling. So this is the type of the expression we get in the second route. And you could notice that what's happening here is before we were putting the shifts into the generator. Essentially, we had I tau plus the shift expression, the shifted value of the amplitude, h, and then plus I tau with the shift, something of this kind, right? But instead now, if we have G written in terms of these simple operators, another idea was to actually not to put this shifted amplitudes into the G. That complicates things, because then we need to get rid of the powers of G, right? So instead, let's try to obtain the gradient by putting the shifts into these simple operators, and I'll hope to get the gradient by selecting the coefficients, right? So like I put in this formula, shift is down to the simple operators, and then the G part left without the shift, right? H. So the expression will be like this. And then we won't need to get rid of the power of G generated by these shifts. Instead, we will be only required to remove the powers of On, and ONs are all presumably simple. Let's say On squared is 1. So that's why it's easier to get rid of the powers of On rather than powers of G. And yeah, so this is ONs are low eigenvalue operators. And then, yeah, we have only plus minus 1. How does this work? If indeed On is just plus minus 1 eigenvalues, then we could easily show that the previous expression for the parametric shift rule, we've simply taken this shifted expression and this, just theta with different signs. If we subtract one from another, because exponential function of On with some theta and plus I, it's let me remind you, it's just cosine of theta n identity plus I sine theta n On, right? This expression. And because of that, you could easily cancel On and only leave on the left and the right sides. And there is an extra coefficient here. So then you can easily construct, but what we want is really the G to be on the left and right side. Now we know how to obtain On the left and right side. All we need is just to add up this type of differences so that we get G instead of ONs. But we know how to do it because G is just the sum of ONs with some coefficients dns. And this is really the solution. We need to just get rid of the sign part and put the dn instead. And this will give us the gradient expression. Right? So that's a simple formula for this operator decomposition. And why is it working generally better? Because it turns out that if you have L eigenvalues, there is an ideal case scenario where you could use only log base 2 operator, the simple operators On, to present the generator. And this is ideal case scenario because, let's say, every operator On has plus minus 1 eigenvalue, and with the different coefficients, if you have, let's say, plus minus 1 one operator pair, essentially one operator, and then plus minus one multiplied by say 10, right? So then the sum of the two will give operator with 4 eigenvalues, and the largest eigenvalue will be 10 plus 1, 11. Lowest eigenvalue will be minus 11, and there will be everything in two other expressions, values in between. 10 minus 1, 9, and essentially minus 10 plus 1, minus 9. Okay? So this will be the eigenvalues of the generator that could be obtained if, let's say, D1 is 1 and D2 is 10. Right? Of course, if D1 and D2 become close to each other, then you may have fewer eigenvalues for the generator out of this sort of expressions. So that's why I said it's an ideal case sort of scenario. You start with G, and then you're trying to represent, essentially, if you're starting with some G that has eigenvalues of some sort, you're trying to find the simple operators, multiply with some coefficients, and regenerate the spectrum of the complicated generator. Right? So not all G's are like that. And but in general, there's a conservative estimate how many operators you need. You could always rely on the Pauli, not a Pauli product. So here P is a projector. You can always rely on the fact that if G has L eigenvalues, so then you could always use projectors as those simple operators. And projectors always, if you want to transform them into reflections, that's what we like to use. Like say, if you have a projector, then the eigenvalues of the projectors are always 0 and 1. And if we want the operator that is having the eigenvalue plus minus 1, we could always obtain that out of the projector by taking 2 projectors minus 1. So that generates the operator that has only eigenvalues plus and minus 1. Okay. So there is this conservative linear scaling possible in the decomposition. Generally, the decomposition is sort of challenging how to do it in an optimal way. Here's an example where if you have, let's say, generator with just a matrix representation with just 4 eigenvalues, 3, minus 1, and 1. So you could decompose it into 2 operators with 3 eigenvalues, 3 minus 3 and 0. Then this point is 0 and minus 1 and 1, right? But also you could decompose it into sort of ideal case scenario is like these 2 operators with just plus minus 1 and plus minus 2 eigenvalues. So this just requires 2 simple operators to present this generator. And as like with even numbers, there are lots of ways to decompose one number into the sum of others. So with the cases of generators where you have multiple eigenvalues, how to present them as like simple operators with few eigenvalues, that there are multiple ways of doing that. You could sort of try different heuristics and find the best solution. Trying these heuristics is not that hard because usually you don't go for the very large number of eigenvalues generators. All right, so just one example to illustrate this as square conserving fermionic generators. There are quite a bit of them, and let's say if you want to say do the excitations, these are single excitations, and these are, let's say, double excitations with unpaired electrons, then it turns out that the number of these, let's say, elementary eigenvalues for various 2-electron excitations could be all the way here in the subscripts is the degeneracy, but the different number of eigenvalues 1, 2, 3, 4, 5, essentially 4 times it's 9, right? So 9 different eigenvalues. And so if we would go with the polynomial quadratic way, then that would be quite substantial number of expectation values to calculate. But if we do the decomposition of these operators in terms of some simple elementary ON operators, which are just similar to UCC excitations, the excitations, then we could go only up to 4 such elementary operators. And then I guess this is just to summarize that you could go about the generalization of parametric shift rule in 2 different ways. One is just using straightforwardly the polynomial expansion of the exponential function. Another is a little bit smarter and uses the shift into just this elementary operator decomposition for the generator. Okay, and the second way usually produces the fewer expectation values for complicated generators. Okay. Any questions? Yeah,
but you do have the issue of the decomposition.
Yes.
So even though the scaling
right.
overall is much better, it's
right.
linear instead of scale.
Right, but
still end up.
No, because as I sorry, kind of the important point here is that this is the best case scenario. The decomposition can give you a log scale, which may not happen, but it could. And the conservative scenario, if you use projections, that will be always linear.
Right.
All right. And so then it's a quadratic versus linear.
So it will always be better.
Yeah, it always will be better.
However, you might run into issues when you want to decompose, right? Like the have more eigenvalues.
Usually decomposition of generator at this level, you could always diagonalize this operator in some representation, small representation. So it's always we're talking about the matrices which are not larger than the 1000 by 1000. Like in the worst case scenario, we had 256 by 256. So the finding this eigenvalues of the generators is not that difficult. Yeah. Usually, it's like if you're not too greedy and they're not trying to create some really large operators as your generators, then you always could do this. Yeah, on all the cases that we see. All right, but all this is nice algebraic work. The main problem practically is still that if we want to do calculation of the gradients, the issue is that some of these generators will have a low gradients. And in any of this parametric shift rule generalization, the small values will come as a difference between large values, because essentially these expectation values are energy expectation values, right? So we will need to measure relatively accurate to get the small value, relatively accurate large values, and subtract them, right? So which is not a good procedure to do, because then really you introduce large error, and currently really there is no solution, at least I'm aware of, for this problem, because well, as we will see next, getting the expectation value of the Hamiltonian in general is a problem by itself, and then you get some noise when you do that, and the gradients obtained as some linear combination of 2 expressions could be very challenging. Okay, of course, one can say, all right, if you are getting small gradients with a large error, that may be not such a big deal, because then you could say, all right, I care about only the generators with the large gradients, and therefore, if the gradients is lower than certain threshold, you just don't really worry about this generator, because this is not something you want to add. Or another alternative would be always to put, instead of using parametric shift rule, try to put new generators close to the Hamiltonian, And that sort of helps because let's say if we have the wave function and we always put the let's say we have a wave function here, and when we're thinking about putting the generator, we always will put it close to the Hamiltonian instead of putting it somewhere inside our ansatz. So in this case, technically, the derivative of energy with respect to theta could be, as we saw, just simply it's a commutator of H with G, so that this is an operator by itself that one can try to kind of evaluate expectation value for. Okay, so in some adaptive schemes, when they select the generator, they put it there, and then when the new generator comes, like ideally, the scheme suggests if you want to keep the number of parameters small, you want to re-optimize the parameters in the ones that you optimized before, right? Because new generators change the optimal values or amplitudes for the old ones. So then the old generators are somewhere in between, and then this trick won't work. So this trick only works if you don't want to re-optimize the ones that are already put there and you already found some optimal values. So if you want to re-optimize them, there's some sort of the parametric shift rule would be needed to use, and then there is this issue of potentially small gradients that come in as a result of the difference between the two large values, right? So generally, gradients are expensive still, I'd say. All right, yeah, so with that, let me switch to the next topic, that is actually how do we do the measurement in the near-term architectures. And what I want to point out from the beginning is that what we have in quantum computers right now, it's very similar to what Stern and Gerland did 100 years ago. And that was, if you remember, quantum mechanics, they just measure the orientation along the z-axis for the spin of or angular momentum in general. They didn't know about spin at that time. It was polarization of the spin along the z-axis. So for the silver atoms that are going through the magnet. And why I say that is essentially, if you, well, this is a, I guess, outline of this section, and we'll get to exactly the explanation of the plot in a moment. But what I want to say is that I decided there are some technical aspects of the measurements that I will skip today, and we will return to them next week because they're beautiful mathematically. But today I would like to just in general give a bigger picture of what are the aspects of the measurement one needs to consider, instead of going maybe too much into some details of unitary transformations that are required to do the measurements. So this is the kind of the outline. Probably I'm not going to be able to finish all of these topics, but we will try to look at them. And so returning to the why do we measure only z operators effectively, and why is this more or less enough? It's well, it's easy to measure z operators. Even Stern and Gerlach sort of already knew how to do it. You just put sort of a magnet in the quantum computers, depending on, of course, architecture is done somewhat differently. And another thing that comes to mind, there are multiple architectures, and usually the architectures which are really good at measuring these z operators are superconducting architectures, because there we could do many measurements within the, well, like say, it's not quite as good as like 1 million per 1 minute, but it's definitely 100,000 within a minute. And other architectures like ions, trapped ions, they are way slower in measurement. So things that you see, they make sense mostly for the superconducting techniques, superconducting hardware, because others have a hard time actually doing millions of measurements, and that's what we will see be needed for kind of doing the even small molecules, right? All right. Now, if we only can measure these, why is it enough? And what do we do with the electronic Hamiltonian? And as you could remember, in the qubit space, the Hamiltonian, the electronic Hamiltonian, is not only just all the z terms, there are x's and y's. And generally, in the situation where, let's say, for simplicity, we need to measure x for the, let's say, qubit 1, right? And we have a wave function or an expectation value like this. So then one can put the unitary transformations like done there, right? So we put the unitary transformation. That whole purpose of that transformation is to make x to be, say, z that we can measure. But then because x is not z, we put u. And then to compensate for this u, we put another, right? And then what this means is that if we need to measure psi function, the x operator on the psi function, instead, we measure z, but on the phi function that is obtained from the psi by putting extra unitary transformation, right? So the kind of in a very simple circuit notation, this would be preparing the psi state and then adding some extra unitary transformation that at this moment prepares really the phi state. And then here, I guess, it's U dagger, right? Because it's the bra part. This is the get point. Okay, and then we could do the measurement of z operator, and whatever we get, if we do this experiment several times, right? So we get we get this z multiple times. I is the number as every result of the measurement. Let's say I goes from 1 to whatever number of measurements we do. We divide this by number of measurements, and this is like our expectation of z. And the estimate of this quantity that we originally wanted to obtain. Okay, so this is how why generally for some simple operators you could only measure z's, and the other operators you could just essentially measure by doing the modification of the system before measuring z's. Okay. One simple analogy would be if you have a ruler to measure the width of the table and it's fixed in the space, you cannot rotate the ruler, but you can rotate the table, right? So by the table, I mean the state, and by the ruler, I mean what we can measure. The ruler is fixed, it's in the z direction, and then we need to rotate the object that we are measuring. Okay? But now going back to the Hamiltonian, it doesn't contain only z's, it contains x's and y's. And the same idea is that we want to then find the unitary that rotates the Hamiltonian into this form where we only have z's, right? So that would be an ultimate solution, and we're done. Unfortunately, the problem is that if someone can do this, this would be equivalent to solving the problem. So we cannot do this because this would be like, since we remember these are in the Jordan-Wigner, they are like occupation numbers, and that would be just figuring out the way how to bring the Hamiltonian to just occupation numbers, and this later determined as an eigenstate, and then yeah, that's diagonal form of the over Hamiltonian solution of the problem. Cannot be done easily. But instead, what people do is to, we could use the linearity of the expectation value. What this means is you could break down the Hamiltonian into linear combination of simpler Hamiltonians, where you can find the unitaries that bring this simpler Hamiltonians to the OZ form or Eisen form, right? And then sum them together to get the original expectation value, right? Because everything is linear in quantum mechanics, so we can use that. Now, these large z's are just polynomials of the z's, the individual Pauli operators for individual qubits, right? And so then the scheme would require, again, building the psi, applying the extra unitaries, and then measuring these. The result will be equivalent of getting the expectation value for the fragments. Then we could sum the fragments to get the expectation value of the full Hamiltonian. That's how measurement can be done in principle. And in the first schemes, people, what they did, first, the most straightforward way, when we go to the qubit space, we have expression of the Hamiltonian in terms of Pauli products, right? So these PNs are, they can be used as HN, right? Because for every Pauli product, it's not like it's relatively easy actually. Every Pauli product would contain some product of X, Y, Z's, right? And we know how to transform X, Y into the Z's at the individual level. For those who we will talk more about the, I guess, gates later, but like Hadamard gate, phase gate, that they could be turned into the Z's, and then every P can be essentially measured using this scheme. The problem with this very simple-minded approach is that there is a n to the fourth Pauli products, and one ideally want to group some of them into the bigger Hamiltonians, right? So that we don't need to do n to the fourth sets of measurements, because for every HN, for every operator we want to measure, you need to remember that the wave function we prepare here, presumably in ideal case scenario, it's an eigenstate of H, right? It's not eigenstate of the things we measure. So that means we'll need to do multiple samplings, right, of each this fragment. And so find the distribution, get the average, that sort of things needs to be done. And if we need to do it n to the fourth times, then it's still polynomial, but it's expensive. So ideally, you want to find the bigger fragments so that you need to just measure those, right? All right, so now that kind of brings me to requirements. What do we want from these fragments? We want these HNs where they could be diagonalized essentially using very simple unitaries, because also we don't want to put too much extra circuit. Also, we want to be able to do this on a classical computer and on a quantum computer, because on a quantum computer, sort of, we put this unitaries as a circuit, but on a classical computer, we figure out, okay, which Z's we need to measure, or what is our polynomial, how do we construct the expectation value of H, right? And then the second requirement is, which is not very clear at this point how to satisfy, but ideally, we want fragments where the number of measurements you need to do to get the accurate expectation value is not too large, right? So generally what happens is that you get when you do the measurement, you get the different collapses of the wave function to expectation values of HN expectation values, and then you sort of bin them. You do this summation, right, where this is going to be the just eigenvalues of HN that you get, and then you're trying to find what's the average from this But we know that, well, we'll discuss this more in details in a moment, but one would like this distribution to be not too wide, right? If possible. How to do that? That's something that you need to think of up front. Otherwise, you end up with too many measurements. Okay. All right. So, but first question is, okay, what Hamiltonians can we actually measure? Meaning that which Hamiltonians can we diagonalize? Because what we want is easy unitaries to be able to bring this to the diagonal form, right? In the quantum computing language, sometimes these Hamiltonians are called fast forwardables, or in a normal language, it's exactly solvable. And depending on here which algebra you are considering, there are multiple heuristic approaches. There is no really known to me general theory of how to determine what Hamiltonian could be exactly solvable using some simple unitaries, because the notion of simplicity is not very well mathematically defined. Usually mathematicians consider, okay, in this class of unitaries, can you diagonalize a certain class of operators? And that's what is done here. Essentially, for the qubit space, there are certain classes of operators which we know which unitaries you need to take so that they will be brought to the diagonal form, to the Z form. And so it turns out very simple class of linear combination of commuting Pauli products is one example. The Pauli products in this linear combination could be also anti-commuting. It turns out you can also diagonalize those. And then there are more general combinations, which I won't go to the details today. Now, in the fermionic case, we actually know from the quantum chemistry that if one construct, let's say, one electron Hamiltonian, then this Hamiltonian can be diagonalized, brought to the occupation numbers by some orbital rotations, right? Occupation and I, epsilon I, U orbital. So we'll talk about how we can generalize this recipe, or maybe going beyond the Hartree-Fock to Hartree-Fock-Bogoliubov. So this is just a different algebra allows you to do different tricks. And then once you formulated, okay, what fragments do you want to work with, you need to find these fragments, of course, in the Hamiltonian, because generally you also face the problem of H being decomposed into linear combination of these fragments that you can deal with, right? So how to do that is also not always straightforward. Okay, so those are two main problems, and let's I guess let me illustrate some of these solutions that I already talked about. One is, okay, if you have a Hamiltonian after doing, say, Jordan-Wigner transformation on your electronic part, and here I'm skipping the coefficients, you could try to use the graph techniques to find essentially linear combination of commuting parts. Because commuting parts, we know how to transfer into the diagonal parts. And why graph problems? Because turns out the commutativity is a binary relation without transitivity, and therefore the graphs are ideal to represent it. So what I mean is that essentially it's like essentially you could think of it as like a friendship, right? So friend of your friend is not necessarily your friend, right? And that's like three operators. A may commute with B, and B may commute with C, but C and A, they don't need to commute, right? So that's why we use graphs. And in order to find fragments where everything, where every element commutes with each other, so we like first construct the graph of the Hamiltonian, connect things which are commuting, and then look for the subgraphs where everything is connected, right? And so there are ways to do it. Actually, originally we were thinking about, again, trying to reduce the number of fragments as much as possible. And that turns out to be a known graph problem called minimal click cover problem. It's because these fully commuting sets, they are called clicks in the graph language. And then if someone gives you a graph and you want to find, like, there are multiple ways to construct these clicks. And it turns out to find really the kind of split of the graph to these clicks in the most optimal way. So with the minimal number of fragments, it's an NP-hard problem, meaning that it's classically very exponentially, essentially hard. Grows, the computational efforts grow exponentially with the number of nodes in the graph, right? But it turns out that there are some heuristics, and we learned later that actually greedy approach, finding like largest graph, subgraph that is fully connected, removing them, and then looking for another fully connected subgraph and whatever is left, is actually working better for the number of measurements. Okay, let me pause at this point, and we will continue after 5-minute break. If you have any questions, let me know.
Jeg tror faktisk, hvis det var det rigtige for kurs løbefrugt, der var, det tror jeg godt, vi kunne. Nej, det er gode eller hvad? Ja, der er nogle af en kurs, det er ikke. Kurs løb? Ja, kurs løb. Nej, og det er dem her, hvad? Ja, der er 2 situationer, der ikke løber. Jeg tror, han har fået den så ud i en som gang. Der er mange nok. Som vi Nej, også det er ikke nok det hurtigt. Nej, det tror jeg. Altså, jeg vil sige, jeg tror, at Theo er okay. I forhold til at det er
Should be all a core.
Så Manuel sagde, han havde været ude for løb, og det var ikke gået så godt.
Space.
Nå ja, men jeg ved hvad, sådan er det.
Du er det ikke.
Jeg ved ikke meget.
Blind ones like me.
Jeg er bare han er ikke sådan rosen og så han har også mange
Not having to reason.
han tager sig til både han har også
Jeg tror også, han har det lyder også nogen har været på spørgsmål i Norge. Ved du hvad, så bliver
altså jeg tænker der kommer mange højere over og syner på.
Nej, også en ting med at skrive senere jeg var på. Altså vi har lige noget her.
Jeg skulle hjem. Jeg kommer lidt til bøller og så lidt på den der.
Jeg vil se hvad
har jeg faktisk det var
ja, måske godt have det, tror jeg.
er det ikke samme hold så tror
Jeg kan selvfølgelig prøve at tage det.
Jeg tænker bare at tage på som at skifte til.
Ja, det tænker jeg også bare.
Det var okay. Nej, det er det var så meget god.
Ja, det er jo ganske overfart det også. Velkommen til København.
ser bare fjollet ud.
Ja, altså jeg skal jo lade en helt anden bus fra universitetsvejen, når jeg skal til Nørreport, jeg skal til Møllepositionen, til Nævnstation. Så det er næsten det samme vej, som vi er fuldstændig. Men det tror jeg godt. Jeg skriver på. Nej, det er ikke
Det der, det er straight up dårligt at gå.
det kunne jeg bare kunne.
Det kunne jeg bare gå.
Ja, det er faktisk ikke engang.
Og lige snart jeg er der, så jeg tror, vi skal gå hjem. I og med, at det er over.
Men er det kommet? Det ser ud, hvor kursen går. Ja, okay, altså så. Ja, det der ting for det der ende.
Det der det ikke page, og det der
Ja, ja. Ja, men jeg går til en gang.
Ja, det var
Ja.
Jeg håbede, det var en bus, der var bedre end at gå.
Det er bare, det scroller over. Det er ofte tidspunkt.
Nej.
Så er der nej. Ja. Altså det. Jeg skal nok have en cykel. Den skal jeg få.
Nej, det tager bare nogle navne. Det er sådan,
Det er faktisk det.
det skal man bare det, når jeg har været til at spørge om det, og det var bare sådan, det er bare sådan, og der er altså ikke noget at gøre.
Det er bedre ikke om man skal være et andet system.
De kan ikke noget det der.
Okay, det kan slet ikke. Okay, jeg troede det var så.
Nej, men altså, IT her er åbenbart ikke styr, fordi det er noget sjovt, kan det ikke universitet.
Det er lidt også.
Det er ikke lige deres kontant. I hvert fald ikke den IT-afdeling, der er selvfølgelig kemi.
Ja. Nå.
Som også er kun 2.
Ja, det er sport.
Ikke 3. Så 3 mennesker.
Men så er det ikke engang sådan, det er universitet.
Nej, det er 7 kemi.
Okay.
Ja. Kemi ting. Malet. Så begynder jeg at logge ind. Så går jeg ned og tager en opgave. Eller noget, så jeg kommer tilbage. Og det er nogle gange på færdig. Hvad gør man?
Nå, det er, hvis man har en substance noget, der er defineret første gang. Ikke
Ja, den.
Ja, det bruger man så over.
Ja, det
Jeg tror, det var det.
jeg kan godt huske, hvad en sidste spørgsmål. Det er så spørgsmål. Ja.
Står der ikke.
Det virker også meget.
Man kan ikke tvinge dem til at lave det der.
Ved du, hvad du gør? Du kan lave en try except runde for den importerer. Og sige try, importere det på den almindelige måde, except module import error, og så kan du importere det på din måde.
Men jeg har jo ikke måden.
Jo, virker det ikke, hvis du importerer det sådan relativ import, i stedet for den absolutte?
Hvis jeg gør det med fil, så laver en fil.
Nå, men hvis du...
Men jeg kan ikke ændre det, så gør det.
Try. Det der. Except. Og det er den her oppe. From.import.
What it is.
All right, let's continue. Good. All right, so this is the one way to find the fragments that we can measure. And then actually, when it comes to commutativity, there are two ways to define it. Well, there is a normal way, which sometimes is called full commutativity, just to separate it from the another way. The motivation will be clear in a moment. So that the other way is called qubit-wise commutativity. So what it means is that we, in the qubit-wise commutativity, look at the Pauli products and only group if not like Pauli products generally commute, but rather they each, like let's say in two Pauli products, the corresponding qubit operators, they need to commute as well, right? So this is an example, x1, y2, and then two other Pauli products that you can group with that is only x1 identity 2 or identity 1 y2, right? Because if you put something that generally commutes with x1 y2, let's say z1 z2 generally commutes, right? But that would be a general commutativity, not qubit-wise commutativity. And the reason for separating these two commutativities is that turns out that will be a discussion of the probably next lectures, is that there is a way to construct unitary transformations that diagonalize both types of commutativity, but the difference between the two commutativities is that in the full commutativity, you generally need non-local rotations, meaning that you may need rotations that essentially act on more than one qubit at once. All right, so that's called non-local rotations. But for qubit-wise commutativity, there is always a way to rotate one qubit at a time into essentially OZs, right? Because at every qubit in this group of qubit-wise commutativity, we have one letter to change because there is no way we could have two letters. If we have two letters, two different letters, then they wouldn't be qubit-wise commutative, right? And so why this is important? Because in the near term, these local rotations, which are single qubit rotations, they are they have larger fidelity. It's like smaller cost in terms of accumulation of errors that the one have if we do local rotations. Therefore, people prefer to these days use qubit-wise commutativity, even though the groups that you can collect, they are much smaller since it's more restrictive commutativity, right? And generally, full commutativity gives you, if you think about it, how many in total powers that can commute in general. In the case of let's say qubit-wise commutativity, that would be 2 to the n. While in the case of its full commutativity, it's kind of generally got 3 to the n. I need to remind myself, but it's exponentially more because we have essentially more things we can combine in the group, right? And I remember from the practical kind of perspective, if you take the Hamiltonian that we have in the fermionic problems, go to the qubits and do the qubit-wise commuting, groups. They generally have approximately 3, maybe a constant number of on average terms inside each group, while this is qubit-wise commutative, and then full commutative, they have on average groups of the size n. So if we had initially n to the 4 Pauli products, that means here we will end up with n to the n cube groups, while here we still end up with n to the 4th groups, right? So this is the size of the group, size of the group. This is the number of groups. Okay, so how to construct these rotations we will discuss later, but it's a very well-known formalism and very mathematically beautiful. Now, with the fermionic algebra, actually this was found first. We can go beyond commutativity, so we can group things which don't commute, still measure them. And to kind of the simple example, which I already pointed out, if we know that any one electron operator could be rotated into just a sequence of linear combination of occupation numbers, and when we go to the qubits, they all turn to z's, right? So the reason for that is, well, we could use orbital rotations. They form a small Lie group, right? Small compared to the exponentially large. S2n, right? So this one is just polynomial because number of generators is just quadratic. And turns out that in general, the fragments which could be diagonalized by small Lie groups, they are very valuable because we could solve these fragments. And the nice general statement here that could be made is that whenever we have the algebra that contains some elements, the algebra, then if your Hamiltonian is a linear combination of these elements, so then there is always a Lie group element that will diagonalize such Hamiltonian. In the sense, it will produce linear combination of some elements of this Lie algebra. Let me call them C's because they all commute, right? And they all commute, and they have a representation that is diagonal matrices, right? So this process essentially is equivalent to diagonalization of the matrices, but in operator language. So operators form, let's say, Lie algebra, and then with certain conditions which are usually satisfied by certain conditions means that these operators all are Hermitian or anti-Hermitian, then the constructed any linear combination with real coefficients, let's say, then there exists a Lie group element U that constructed from the as a product of exponential functions of that Lie algebra, some coefficients, some amplitudes here, that will sort of bring this linear combination to another one that contains only terms which commute, CK, and then they can all essentially be represented as diagonal matrices. Okay, and it turns out in Lie algebra language, this C, let's say C is a set of CKs, and it's a subset of original Lie algebra, and it's called Cartan subalgebra. Cartan subalgebra. Algebra. In the case of fermionic algebra, these guys generally form the algebra, and occupation numbers, they are examples of Cartan subalgebra because any occupation number commutes with any occupation number. And this is technically, it has a name. The statement is called maximum torus theorem in the Lie group Lie algebra theory. And it's you could think of it as a generalization to operators that are formed in Lie algebras. It's a generalization of what we know in normal linear algebra is that any normal operator will be diagonalizable. So you can always find the unitaries that diagonalize normal operators. So this is practically the generalization on the operator case. Okay. And so this is what we know in quantum chemistry, that any effectively one electron operator could be brought to the diagonal form if you use orbital rotations. Okay. Of course, this doesn't stop at the fermionic. You could go and apply this to the qubit space as well. So there in the qubit space, one can say that, all right, so for every, essentially for every qubit, if we have a, like, let's say S, for the simple case of SU2, the one qubit case, we can diagonalize any operator, which is a single qubit operator, like alpha sigma x plus beta sigma y plus gamma sigma z, right? I could put identity if you want, but this could be always brought to the form with a single qubit rotation that contains only sigma z, essentially. Like you could always say this is a sigma z with some constant because there is only you could also diagonalize this into sigma y or sigma x. Generally, in this SU2 Lie algebra, you could form Cartan subalgebra either from having sigma z or sigma y, sigma x. They all equivalent because after all, the formal definition of this Cartan subalgebra is the maximum subalgebra of the algebra that contains only commuting terms. And in SU2, it's only a single term. While in the one electron algebra, we have very many occupation numbers, so they all commute. So we have Cartan subalgebra, which is bigger. In a single qubit case, we have only one element. Usually it's selected to be sigma z, and this is always true. Now, I guess the nice thing about this is that we could say that it's always can be done if you find such unitary that is a product of that q sigma q, right? So it just needs to be, you need to have rotations with the corresponding Lie group element. Okay. So now, how is this? This is all great, but how is this useful if we want to deal with the 2-electron Hamiltonian, right? So this is not very useful for us because this is just 1-electron case. Now, the way to generalize it to 2-electron case is to take the linear combination here and substitute it by quadratic. Okay. Why is this useful? Because when we do this substitution, then it's we're generating the 2-electron operator. Why is that? Because the unitary orbital rotations apply to occupation number of any kind, right? So if we do this, then it turns out that this will be generally this operator is PQ, alpha PQ, say, where EPQ operators, just A dagger P, AQ, right? So this is generally true. One can see this because any orbital rotation can be written as simply sum, a single exponential expression with the sum of E PQ with some coefficient CPQ, let's say here PQ, and then if this is our unitary, then the conjugation will give us, let's say, here different index and k. Then here we'll have sum of PQ, PQ, CPQ minus. So this, as we know from the Baker-Campbell-Hausdorff expansion, what will happen is that we will have nk plus nk with the sum of PPQs, CPQs, plus n with sum with another sum divided by 2 plus and so on, right? So the typical BCH expansion. Why we're getting only a single electron terms? It's because these occupation numbers, when you form the commutators with the 1 electron terms, it's again 1 electron term, and then this one will be 1 electron term with another 1 electron term, still 1 electron terms, right? So you cannot get outside of the 1 electron terms, and this is what we have here. It's a different question how to obtain the alphas, but there are ways to do it. And just generally, in this case, if we put 2 n's, then we generate for each n 1 electron sum, and then we will get some form of 2 electron operator, right? So if we have np and q here, then this will be 1 and another sum rs, maybe we want to keep that different with some also coefficients rs, right? So, and this is, if I write this down as now double sum of PQ RS with EPQ ERS, and then some GPQ RS, some coefficients. So, and give you this, you won't be able to tell just by inspection that this came actually from something as simple as occupation numbers transformed using just single orbital rotations. On the other hand, this is convenient operator to measure because any occupation number will turn into the z's. So if we go back to the qubit space, this type of fragments could be measurable as long as we could put the unitaries in this form on a quantum circuit, then we could measure the occupation numbers. Okay. And what else? Important here. It will come. Right. So how do we now find these sort of fragments inside the Hamiltonian? Because the Hamiltonian, even though it looks like this, but it doesn't come from orbital rotations applied to occupation numbers. If it were the case, then all the eigenstates of our Hamiltonians would be Slater determinants, because these guys, these individual fragments, you can always solve by finding orbital rotation where Slater determinant is an eigenstate of that fragment, right? And also, if you do Hartree-Fock on this sort of 2 electron Hamiltonians, Hartree-Fock will always produce the exact answer, because Hartree-Fock will always find the rotations that will make this will find the eigenstate of this Hamiltonian. Okay. Now, how do we find such fragments in the H? We could simply make sure that if we take the two electron integrals from the real H, right? So that when we do this procedure with different orbital rotations and different coefficients in this quadratic part, so we can recover the two electron integrals in the H, right? So we could just do the norm minimization. For that, we need maybe multiple fragments, not a single fragment, but few fragments. But it can be done as like a nonlinear search, and with polynomial number of parameters, always can be done. Now, this is nonlinear, but there is a simpler actually approach. It also was produced in the literature before our more general consideration. And this simpler approach, what it does here, one can, in order to go to the two electron solvable problems, one can just square the one electron Hamiltonians, right? So that also is going to generate the two electron one, but the structure of this complete square will be simpler than what we have, because in the complete square, essentially, you make a square of the linear combination. And so the coefficients in front of the quadratic occupation numbers, they are effectively, you could think of them as a matrix, but it's a rank deficient matrix because it's coming as an outer product of the vector epsilon, right? Epsilon is the coefficients of the that vector, and but it turns out that this form, this decomposition, could be obtained easily by starting with the two electron integrals in the Hamiltonian and just doing either SVD, or since it's a sort of a symmetric matrix, if you consider it as a matrix of PQ and RS, you could do the kind of diagonalization that actually leads to fragments like this. There will be multiple fragments again, not more than n squared, but you could obtain these fragments easier than maybe this nonlinear search that we're doing. But nonlinear search gives you fewer fragments because our lambdas usually are more like it's a full rank matrices versus like rank deficient fragments here. Okay. All right. So now another important aspect, even I guess one of the most important aspect of all this is and we learn, unfortunately, this is a hard way. So it's a number of measurements, because after all, it's not so much, as it turns out, about the number of fragments, but it's of the final figure of merit is how many times you need to measure. All right. So, and there is some statistical theory that we need to review very quickly. It's not that complicated, but it's very important because, as I said, I just remind you that we're measuring eigenstates of not fragments, but maybe not even the Hamiltonian. But yeah, so we're preferring the states which are approximate eigenstates of H, but they definitely not eigenstates of fragments that we're measuring. And then we would like to minimize the total number of measurements. And let's start with a simple example, which would be, imagine the case where your H could be split in two. The ones, this H1 and H2 are the measurable fragments. And the question is, all right, so what's the error in the process if you obtain expectation value of H1 with the M1 measurements and H2 with M2 measurements? It turns out that if you do that separately, it's independent measurements, then the total error on the expectation value of this H with the total budget of measurement then will be given by this expression. Okay. So where does this expression come from? One may wonder. And let me just quickly illustrate what's going on here. So what's going on is application of so-called central limit theorem, because what we do when we construct the estimator for the expectation value, we take very many sort of results of measurements for individual. Let's say we have H1 expectation value that is obtained by summing H1 individual wave function collapses M1 times divided by M1. Right? So that's H1, and then we can do the same for H2. So we can put K here, K is 1 or 2. Right? All right, so this is our estimator, and it turns out that this, no matter, or like if your number of measurements is not infinite, this one is always going to be different than quantum expectation value, right? That we can obtain if we know the wave function and we know the operator. Potentially, we could just brute forcefully calculate this, and this estimator should converge to the true quantum expectation value, right? But with for the finite number of samples, MK, there will always be difference between the two. And according to actually central limit theorem in statistics, this estimator will deviate from the true average by the normal, like essentially by the deviation. We can always produce the probability of this deviation between HK estimator minus the true value of expectation value. If we want the probability of this deviating more than, say, K times sigma of H bar K, K is probably not as let's say small, well, M is also taken. Let's say J. All right, J times sigma. So that is given by some like integral 1 minus from minus J to J of the Gaussian. Write down. Yeah, it's minus
R minus the.
Yeah, well, it's minus z squared divided by 2ez in normalized variables. Yeah, divided by 1 over 2 pi here. So these are maybe somewhat unnecessary details, but the point here is if we want, let's say, 3 sigmas, J is 3, then the probability of deviating from the true value will be less than %, right? So the 3 sigmas gives us 99.7% being within the range, right? And that's how well, we could essentially say that, okay, with 3 sigmas it's enough, and like the only thing we need to now connect is the sigma of H bar K. Sigma of H bar K is the essentially square root of variance of our H bar K estimator, and one needs to just connect this with the variance of the true quantum variance that we can calculate technically from first principles. So if we now know how the H bar is connected to H, right? It's just divided by the number of times we measured, and therefore we have here square root of variance of HK operator divided by square root of just the number of measurements my, because it's all kind of independent measurements. So M K, sorry, K number of measurements, right? So what this tells us is that technically with free sigma we have error that is well, this epsilon that we have is, let's say, 3 sigma h bar, right? And that error is equal to sigma k is the 3 variances of square root hk divided by mk. And then the epsilon k squared is 9 variances of h divided by mk, and mk squared. Oh wait, no, I think I forgot the square root. Sorry, square root here is necessary, and here don't have square root. Yeah. All right. So this is the error, and then the 9 is kind of dropped here. So we this is just a constant. So our generally error of the estimator will be related to the variance of the operator that we're measuring, and it could be reduced by increasing the number of times we do the this experiment for the measuring the fragment. Okay, and then the total epsilon square is epsilon 1 square plus epsilon 2 square. It's the independent measurements and of the independent parts. And that's how this essentially formulas come into play. Now, central limit theorem allows to have random variables, which these guys are, from any distribution. So it's not like we are requiring that the distribution of eigen, essentially the results of the collapses of the wave function should be distributed normally. They can be distributed anyway. It's just if you sum a lot of them, they all come from the same identical random distributions, right? So then this quantity will be distributed normally. That's why we use for the error normal distribution. Okay. And then essentially the bottom line here, we depend on the variance, and well, we could reduce the error by increasing the number of measurements, but we don't reduce it too much. As you could see, epsilon, like it would be ideal if for epsilon we have m, but instead one can say that epsilon scales with the square root of m, right? So because epsilon squared is corresponding to inversely proportional to m.
So you have to reduce the variance.
Yeah, you either reduce the variance or increase the m. Yeah.
So are we always guaranteed that the assumption of the central limit theorem will be guaranteed? So for example, that those HKs, the distributions that will have second moments, right?
No. That's what I was trying to say. Let me state it as kind of more explicitly. For central limit theorem, you could sum random numbers from any distribution.
It's not really any. The second moments have to exist.
No.
So for example,
okay. In that sense, yes. In the sense that.
So if you have a heavy tail distribution, it might be like Lorentz, for example, right? Distribution that will not be satisfied.
The fact that the moments of these distributions they should exist, right? Yeah. But we are working with a kind of Hamiltonians that have a in a finite space. Operators in a finite space, they have a finite spectrum. And then any variance or any other moment will always be finite. So it always will exist. All right. So we don't require these coming from the distributions where there's only first and second moment and others are zero. They could be any, but as long as they exist, right? And then the fact that we are summing individual random variables, that guarantees us the applicability of COT. And we could use this for the estimating the error using variance. All right, so now, yeah, essentially one more step here is, okay, one can ask the question, if you want to reduce the error, so how to distribute the measurements between the fragments, and that is a relatively conceptually straightforward problem of Lagrange multipliers, right? So if you have two variables, they sum to m, and then what's the optimal distribution of these m's between the fragments? Turns out this formula can be obtained, and it shows that intuitively clear picture that the fragment that has larger variance should be more measured more, right? So that's nature of, if you want to reduce the total error from this formula, you want to increase the denominator for those whose numerator is large, right? And so that's what Lagrange multipliers give us. And if we put all together optimal number of measurements, if we select these measurements optimally according to this ratio, right? Then the optimal number of measurements will be, for achieving error epsilon, will be like this. And what this actually give us, it's a little bit of I guess optimistic picture, because in general one can say we don't know this variances exactly, right? So because the wave function we are constructing, it's on a quantum circuit, and it's a complicated wave function. Otherwise we would do quantum computing if we could do this wave function on a classical computer easily. So we don't know these variances exactly, but we're using the knowledge of variances in order to do this partitioning optimally, right? In that sense, this estimate of the total number of measurements is somewhat optimistic. It's considering that we knew the variances exactly, and we distributed our measurements optimally. But in many cases we studied empirically, sometimes, and you'll see it in a moment, that sometimes if we want to know variances, we could use approximate wave functions to estimate variances. Like, let's say if we're building like some complicated wave function, we may try to use RTFocus, CISD, some classically optimal, some classically efficient ways of generating approximate wave function to just estimate variance. Okay. Now, what this formula also sort of teaches us is there is a certain algebraic form, like this square. Essentially, if you have more fragments, it's always sum over square roots, but square, right? And that form actually, if you do a little bit of algebra, it's easy to show that uneven distributions have kind of smaller number. Like if you split your Hamiltonian to fragments where some of the variance will be large and some of the variance will be small, with the total sum being the same. So then these uneven distributions will be better in terms of number of measurements. The reason for that is you could, with the simple algebra I mentioned before, is that you could massage this expression a little bit by introducing these weights for individual variances, right? So you kind of take the ratio of the variance of each fragment to the sum of variances. You get the expression something like this. And it turns out that this term here, sum over square roots of opposite, like weights from different fragments, it will have the form like this if you have just a case of two fragments. And it's a lot like Shannon entropy, essentially. So this function peaks in the same place as this function. That can be shown. And what this means is that the worst case scenario is that all the weights are the same. Okay, because entropy will be the largest, and we want it to be smallest. So you want to be either here or here. You don't want to be in the middle, right? So democratic splitting of all the fragments to be of this kind of the same size or the same variance. That's the worst case scenario. And yeah, they pick at the uniform distributions. And where I'm going with this is that if we apply greedy algorithms to select our fragments, empirically, it kind of makes sense based on this algebra that when you do the greedy algorithms, the first fragments are usually the biggest, and then it's getting smaller and smaller and smaller, and that is beneficial for the number of measurements, right? So, but of course, this is just a kind of rationalization of what we saw empirically, that the greedy algorithms work better than the cases where we try to, let's say, reduce the number of fragments. In that reduction of number of fragments, very frequently we got fragments of the same size. But we could do better if we know this. We could try to find now fragments with the smaller variances, technically, right? So that would be ideal. And how do we do this? Well, there are few ways to do it. The most optimal way, or the kind of the easiest, otherwise you could of course do nonlinear optimization, thinking about two things: that your fragments sum up to the h and the variances will be small. That is usually complicated. So what is easier to do is to have fragments and then maybe move certain things between the fragments so that the fragments still sum up to h, but you could vary the variance by moving things between the fragments. All right, so that simple idea is illustrated here. So let's imagine we have a Hamiltonian that contains only 3 Pauli products, and they commute according to this line. So Z1 commutes with Z1, Z2, and Z1, Z2 commutes with X1, X2. The coefficients is on top, right? And what we can do, we could form 2 fragments. One is this, and another is this. But the middle guy could go like in 2 groups, right? And the coefficient that this guy enters the second group and the first group, the only condition is that they need to sum up to the coefficient that it is Hamiltonian, right? So we could use this split of this middle Pauli so that we could minimize the variance, essentially, right? If we can have estimation of the variance on some simple wave function, then we could optimize the C without jeopardizing the fact that if you sum the 2 fragments, you always get the expectation value of the Hamiltonian, because no matter how you split, you could make it negative if you want, right? The variance will change for the 2 fragments, but the expectation value always will be the same, because yeah, so expectation value is linear, but the variance is not linear. That's what we're playing with here, right? And we have these 2 schemes. One is somewhat simpler. Another is this exactly what I just described: coefficient, so-called coefficient splitting, and they improve the variances that were coming from the, say, forming the commuted sets of Pauli products. But okay, so changing the fragments to lower variances, it turns out we can do even more than just splitting the ones that splitting the coefficient of those which can be shared. Why not to introduce a Pauli products which were not even Hamiltonian? But potentially can do that. We call them ghost Pauli products, right? So we can add to one fragment the Pauli product with one sign, and in another fragment the Pauli product with like a just opposite sign, so that they cancel at the end. But the idea is to reduce variance even more by this simple kind of course, the trick requires you to put something that commutes with the surrounding, right? So you cannot put something that doesn't commute, and or at least not in this scheme.
Is that, can you think of that kind of a little bit like a resolution of identity?
Yes, yeah, right. So it's like resolution of zero, I guess, if you think about expectation of, right, so it's linear. Okay, and then in the fermionic case, it's harder. Initially, we sort of struggle how to reduce variance. We tried exactly what I was describing as a difficult protocol, trying to make fragments which sum to H and also reduce their variances. And then it's not clear how to really well, efficiently do that, because there are lots like nonlinear parameters, since the lambdas are linear, but orbital rotations are not, and we struggle with optimization. So instead, we realized that later, after figuring out this how to do it with Pauli products, we realized that in fermionic algebra, there are similar expressions that can be moved between the blocks. Okay, and it turns out it's again the power of the algebra is very useful here. We call this fluid fermionic fragments, and they're based on the fact that if we just focus for a moment again on the one electron parts, they form the algebra. So that means if you take any one electron Hamiltonian and you add another one electron Hamiltonian, you get one electron Hamiltonian. And we know that there is always orbital rotation that will diagonalize that one electron Hamiltonian, right? So there is a closure in that sense. So you could collect as many one electron terms, you always will be able to measure them, okay? So what do? We take the 2 electron fragment and use the fact that the occupation number times occupation number, it's a projective. So it's essentially this 2 electron looking expression actually is 1 electron. And so in every 2 electron fragment, we have part that looks like 2 electron, but it's 1 electron. And so we take that part where P and Q are the same, and we can take as much of that part as we want and collect into the 1 electron part. So we could remove as much as we want of this quasi 2 electron, but really 1 electron term, and combine them according to what is good for the variances, right? So it's not like we freely can move things between the fragments. Instead, from each fragment, we can take the 1 electron part and collect into one electron fragment that we can measure at the same time. Yeah, essentially. And that's the optimization. But what's nice about this approach is that no matter how much we take, we don't need to worry about the fact that now modified fragments won't sum up to the total Hamiltonian, because it's again, we're just removing stuff from one fragment, and we can always combine 1 electron's parts into just a global 1 electron fragment. Okay, so that made the whole thing much easier. And now I guess we'll show the results. Now just to summarize that we have this qubit and fermionic techniques in general. The qubit techniques, they could be used using qubit-wise, so full commutativity. And in the fermionic case, you could either do this low rank decomposition, which is simpler, but has more fragments, or full rank, which is nonlinear optimization. And then you could kind of optimize the variances if you want further. And generally that helps, either using this shareable Pauli products or fermionic, in fermionic case, repartitioning the 1 electron terms. And at this point, before getting to the results, I wanted to say just a few words about another technique that came after we played a lot with the fragmentation. It was called classical shadow tomography. And it was very surprising for us, because that approach looked at the same problem, but somewhat differently. And the idea was that, okay, you want to measure the Hamiltonian. What you do is you rotate your wave function and then do the measurements. Then you sum up, and then there was a way to sum the results, and then the results somehow magically were producing the expectation values, and then it wasn't clear for us why this is actually working. And to make it, I guess, in somewhat simpler terms, what's going on here is I want to just say that your Hamiltonian, if you apply essentially some unitary rotations, like here we're talking about Clifford group rotations, which I didn't introduce yet formally, but in general, yeah, maybe it's a good time to mention this. There is a Clifford group rotations, and they are the same Clifford groups that are essentially able to diagonalize or bring to diagonal form any linear combination of Pauli products. Right, we'll talk about them more. But what defines Clifford group is this property that any Clifford, any unitary that is Clifford unitary, when you apply it to the Pauli product, you get back some other Pauli product. So that is what defines the Clifford transformation. And as you can see, in case of commuting Paulis, there are such unitary from the Clifford group that will trade Paulis that are in the group, in this commuting group, to so the coefficient even will stay CK, but the Paulis will turn all into the let's say Pauli product of Z terms. So they all sort of diagonal now using there is such Clifford unitary that does that if under condition that of course Paulis in the original linear combination they were commuting. Okay? So that's the condition. And then what in this shadow tomography is really done is choosing random unitaries from the Clifford group, applying them to the Hamiltonian, so and then doing the measurements effectively. So what happens in reality is that when you apply random unitary, then the number of Pauli products in the Hamiltonian stays the same, but the Hamiltonian transforms into, well, there will always be some part, maybe like this trivial part, like it's only Z terms, and there will be part where not entirely Z terms, but X and Y's as well, right? And because you collapse the wave function, it's like on a product state, what you learn about the Hamiltonian in this frame is the Z part, because this part on the any product state we already saw yesterday, it's always going to be expectation value will be 0. So you don't learn anything about this part. You only learn about the part that turns into the Isaac part, right? So this is how this classical shadow tomography works. Why it's called shadow? Because the shadow comes from the kind of projection, creates a shadow, right? And so choosing different unitaries, you create in different shadows because the space is multidimensional. And so you could create different projections. Some projections, according to this consideration, may give you a large part, Eisen part, from where you learn a lot. And some projections may give you bigger non-Eisen parts, and then you don't learn much from them, right? And so for us, from the beginning, this protocol was very magical in the sense that, well, I didn't like coming from the deterministic electronic structure, I didn't like the randomness that they put there. And I didn't really quite understand how eventually they get what well, they claim they get, like the expectation value. So that we'll talk more later, but at least this point kind of shows you that this may not be the most optimal way, which community realized later, but at least it's not that far from what we're doing in the when we group, because one can say that they just come and apply unitary to the entire H, and there will always be part of H that they effectively diagonalize by this unitary, okay? But why not to start with H and figure out which unitaries you need to diagonalize the parts of H, right? And so don't try random unitaries, try those unitaries that diagonalize the biggest parts and then use those, right? So for us, that was the kind of the message. And it turns out later, after people try that, seeing that for a single operator, it's not always good to do this because you don't learn much sometimes. Then they start doing derandomizations, and effectively these derandomization schemes, they are more or less the same as a grouping, because they try to find the unitaries that will put into the Z form the biggest part of H, right? So it's just coming from a different angle, which was not clear from the beginning. That's a shell tomography, which you may have heard about, but many people I've talked, especially in chemistry community, they were kind of surprised how does this whole thing works. But I think the best thing to look at this is just, or maybe for us, because we're coming from the grouping, it's just putting the unitaries and getting information about the diagonalized part, okay? And let me stop here because it's time to stop. And I'll talk about the results and some technical aspects later, okay? That's great.